So what do you get when you mix the incredible predictive power of machine learning with the fundamental rules of our universe? Well, today we're diving into how that exact combination is about to completely change, well, everything.
All right, let's kick things off with a really big question, the kind that drives whole scientific fields forward. What if? What if we could just sit down and design the perfect molecule for any job you could possibly think of?
And we're not talking about some abstract lab experiment here. We're talking about building brand new medicines to fight diseases, designing materials for incredibly efficient solar panels, and literally inventing the tech for a cleaner, better future. This is the big promise.
Okay, but there's this huge, massive wall standing in our way. The way we've traditionally discovered new materials is just painstakingly, agonizingly slow. So slow, really, that a lot of our biggest discoveries have felt more like happy accidents than some grand design. And that right there brings us to our first big idea, the Grand Design Challenge. This is all about getting to the bottom of what scientists are really trying to achieve here. Okay, so at the very heart of materials science, there are really two fundamental questions. The first one, the forward problem, is something we're actually pretty decent at. You give us the structure of a molecule and, with enough computing power, we can figure out its properties. But the real prize, the holy grail, is the inverse problem. That's when we start with the properties we want, like, say, a material that's super strong but also super light, and then ask, what's the exact atomic blueprint we need to build it?
See, solving that inverse problem is the absolute key to what scientists call rational design. Think of it this way. It's about shifting from just, accidentally stumbling upon useful stuff through endless trial and error to an age where we can invent materials on purpose, on demand.
So if rational design is the ultimate goal, what's holding us back? Well, the answer gets really, really small. It lies in the universe's ultimate rulebook, and it creates what we're calling the quantum bottleneck. That rulebook is quantum mechanics. These are the fundamental laws that control everything that happens down at the level of atoms and electrons. If you want to know how a molecule is going to behave, you have to play by these rules, period. There are no shortcuts.
And the star player in that rulebook is the Schrödinger equation. Just think of it like the master key for chemistry. If you can solve this one equation for a molecule, you unlock everything. All its secrets, its energy, its stability, how it's going to react, the whole shebang.
But here's the kicker, and trust me, it is a huge one. For all of its power, we can only solve that equation perfectly, exactly, for the simplest thing imaginable, a single hydrogen atom. One proton, one electron. That's it. For anything more complex, we're talking even a simple water molecule, let alone a new drug, we have to start using approximations. And those approximations get really, really expensive, really, really fast. Just look at this table. Forget the names of the methods for a second and just look at that computational cost column. N here is just the number of atoms. For the most accurate methods, the cost grows by n to the 7th power. So what does that actually mean in the real world? It means if you just double the size of your molecule, say from 10 atoms to 20, the problem doesn't get twice as hard. It gets 128 times harder. That right there is the quantum bottleneck.
All right, so if brute force can't just smash through this quantum wall, we need a smarter way. Maybe a shortcut. And that is exactly where machine learning comes in, offering something like a tunnel right through the problem.
And the core idea, which comes right from the research, is that you can train a machine learning model to basically learn the rules of quantum mechanics so well that it can just skip the hard parts. It shortcuts the whole process and just predicts the properties directly. See, the old way was all about brute force. Every time you had a new molecule you wanted to check, you'd have to fire up the supercomputers and just grind through that impossible math, one by one by one. But the new way? It's a totally different game. It's about pattern recognition. Instead of solving the math from scratch every single time, you teach an AI the deep patterns with a few really good examples. And once it gets it, it can make predictions for new stuff almost instantly.
And this analogy it hits the nail on the head. A traditional quantum calculation is like an old-school chess computer, It chugs along trying to calculate every single possible move. It's powerful, sure, but it's slow and rigid. The machine learning approach is like a chess grandmaster. She doesn't have to calculate everything. She just glances at the board, recognizes the pattern, and knows the best move. It's learned intuition versus brute force.
Okay, so how in the world do you actually teach an AI the rules of quantum physics? Well, it's all about building the ultimate cheat sheet for chemistry. Well, it really boils down to 3 main steps. First, you just bite the bullet. You do a handful of those super expensive, gold standard calculations to create a small but perfect set of data. Step 2, you feed that perfect data to your machine learning model. Its only job is to figure out the deep connection between the structure and the property. And finally, step 3, you use the shortcut. Now that trained model can spit out predictions for totally new molecules in a fraction of a second.
And I want to be super clear about something here. This isn't just random guesswork. These AI models have physics baked right into their design. For instance, the AI already knows that the laws of physics don't care if you rotate a molecule in space. By building in this kind of prior knowledge, the models become way more accurate and need a lot less data to get the job done.
And all of this brings us to the really exciting part. What does this mean for the future? We are, and I mean this truly, stepping into a new era of creating materials on demand. I mean, just think about what this suddenly unlocks. We can simulate how molecules actually move and dance around on scales we could only dream of before. We can discover new drugs in a computer instead of a lab. We can design the perfect materials for better batteries and solar cells, or create new catalysts to make our industries cleaner. We can finally, systematically explore the gigantic universe of possible molecules to find exactly the ones we need.
So when you put it all together, what you're looking at is a massive, fundamental shift in how we do science. We are moving away from an age of just getting lucky and stumbling on things and into an age of rational, intentional, targeted design.
So, I'll leave you with this one final thought. For so long, we've been trying to translate the incredibly complex language of molecules. Now, thanks to AI, it feels like we're finally becoming fluent. So the only question left is, now that we can speak their language, what are we going to ask them to create for us?